that we have been rewriting the last 6 months or so. So I spent a lot of time in Spark. For the meeting today, the topic we closed on basically is designing CosmosDB workloads for throughput and cost efficiency. What I want to cover in the slide deck is basically trying to make clear in which use cases CosmosDB is actually a good fit and in which use cases it isn't, basically. And then going through some of the configuration decisions and trade-offs between basically enabling some capabilities or features and also the cost side of things to basically allow you in potential workloads to identify whether CosmosDB would be an option, and if so, maybe remembering some of those trade-offs and seeing that you ideally come up with a configuration and architecture that fits your use cases without being too expensive. The last part of my presentation will be a little more technical. I want to go through a couple of best practices, especially for data modeling practices in NoSQL use cases. But I'll probably interrupt before so that we can also do some questions and answers before we drill down into some topics that might or might not be interesting for people. So I'll evaluate on the fly a little bit how deep we want to go in those best practices. Other than that, if anyone has questions, like raise them in the chat window. We can interrupt in between and answer questions. I'm perfectly fine with it. I might need some help because I might just oversee those questions.
I'm going to moderate it, so don't worry about that. Yeah.
Okay, perfect. Then I'll turn off my camera and we'll start going through the slide deck, basically.
Perfect.
Okay, so agenda, I'll talk a little bit about it already. I'll start working, basically giving an introduction to CosmosDB. I'm not sure how familiar you are. I'll try to keep it brief enough so that people who have worked with CosmosDB are not too bored, but trying to set enough context for folks who haven't worked with CosmosDB yet. CosmosDB is an Azure data service which provides basically a NoSQL database as a managed service. I think one of the key capabilities of CosmosDB is that it enables you via turnkey global distribution. So you can enable replication into pretty much every Azure region. CosmosDB is a so-called Ring 0 service in Azure, so it's available in every single Azure region, whether it's in the public cloud or in any of the government clouds and so on. And if you start your data in one region, you can basically just via configuration also enable replication, and the data will be available in other regions. The other thing that's pretty unique for the CosmosDB data service is that we have our core API, what in the slide deck you see as a SQL API, which is basically the core API that the service is built on. But we added abstractions to enable via protocol for some other APIs, like Azure Table API, where your data is actually stored in Cosmos, but you can basically point an application that used Azure Table Service before and point it to the same endpoint in Cosmos and use the data as if it was Table API. And the same is true for Cassandra, Mongo, and Gremlin. And I'll go a little bit into the different APIs. The other thing that is pretty unique to CosmosDB is we have a pretty extensive SLA, both for availability, for the failover scenarios, and for the different consistency models that we provide. And most importantly, we also have an end-to-end latency SLA, which means that for point operations of documents up to a certain size, as long as your application is co-located, like in the same Azure region as your data service, we promise a 99th percentile latency of less than 10 milliseconds for read or write operations. And that there are very few other services that promise the latency and the SLA with financially backed guarantees, basically. So I'll go a little bit on. I'll dive into that a little bit deeper as well later. But that may be as a big picture. It's a NoSQL service, and I'll go a little bit into the NoSQL versus relational database part later. But it's a NoSQL service. We provide several API surfaces, so it's usable from different APIs in your applications, and it's providing global distribution as one of its core capabilities, basically. Yeah, one thing I wanted to call out in the beginning. So the fact that we call our core API the so-called SQL API is a fact because CosmosDB, like I mentioned, is a NoSQL database. Like we call it not only SQL. It's that means we have a query language which is it's like you can basically use SQL to do queries against the CosmosDB database. But it's still a NoSQL database optimized for horizontal scale. And it's very important when looking at workloads to not think about like using a data model that has been used in a relational database and one-to-one transfer it into a NoSQL database. So this is true for CosmosDB. It's true for other NoSQL databases as well, simply because there are some patterns that are not working the same way in a NoSQL database like in a relational database. For example, a couple of things I wanted to call out is that distributed transactions, for example, across tables, is something that most NoSQL databases intentionally don't support or have very limited support for it, because NoSQL databases have been built and designed to support massive scale, and distributed transactions are hindering massive scale, and so they haven't been designed to support it very well. And so if applications are relying on it or need it, it's not possible to move from a relational database to a NoSQL database without making some design changes. And that is something that's important. Even when the API is called the SQL API, it's not for a relational database. But some of the design considerations need to account that it's a NoSQL database, basically. Yeah, and then the warning is like, I think the main scenario where customer might get frustrated when trying around with CosmosDB is when they have a relational database mindset and try to migrate a workload one-to-one. And for the reasons I mentioned above, that often doesn't work very well. And there's a learning curve to basically understand how to design for NoSQL databases. Next part, as an introduction, I wanted to just call out like some of the common use cases where CosmosDB is used by our external customers, but also within Microsoft by other Azure services or business divisions within Microsoft. One of the, because we have those latency guarantees for point operations, one of the main scenario is OLTP workloads, like in commercial space, order management, payment processing, pricing engines, real-time recommendation engines, inventory management, product catalogs. Those are very typical scenarios. In another part where CosmosDB is also used is for IoT scenarios. Because CosmosDB provides massive scale and guarantees SLAs for latency and availability, it can be easily used as a sink to insert events like device telemetry or using it as a device registry. And it's also pretty commonly used for digital twin scenarios, like where basically you use event sinks to store raw events, but then you have a digital twin where you have the latest state of certain devices stored, and that's often a view that's used in many other applications with high throughput, and so that's a very typical scenario where CosmosDB is used. Financial services also OLTP scenarios, just with different specific forms than for commercial scenarios, similar for gaming. And may be interesting because it basically shows the commitment of Microsoft to the product. Is where are we using it within Microsoft? And some of the products that use CosmosDB is Teams. Teams, for example, uses CosmosDB to store chat messages that I used in IM, and also for metadata for meetings, etc. Xbox, like I briefly mentioned before, I've worked on Xbox licensing before, for example. So we initially had a database on premise, and then we had to wanted and had to migrate into the cloud. And so when we picked the servers to move to, we also decided on CosmosDB. And I started getting to know about the product basically while I was working on the migration from our on-premise database, which was basically 20 clusters with SQL Server with the custom partitioning scheme. And when we moved it to the cloud, many of the data handling scenarios were much simpler because it was just a hosted service and we didn't have to worry about it ourselves anymore. Xbox is also using it for authentication, for order management, like order processing. AAD is using CosmosDB, not exclusively, but it's one of the services they use, for example, for login scenarios. Office 365 is using it for Office 365 subscription management, and that can be tricky sometimes. Even our internal incident management tool is having a dependency on CosmosDB, which means if there's any issue with CosmosDB, it also means our own internal incidents can be impacted, which was yet another push for basically increasing SLAs and making sure we have as much robustness as possible, because all of Azure is basically using internally this incident management tool. So far, the introduction. If there are any questions, just let me know in the chat window. Otherwise, I'll proceed. So one aspect I wanted to drill down into is basically CosmosDB, like I mentioned, allows you to have a turnkey way to distribute data into multiple regions. Part of that is that when CosmosDB was built initially, it was mainly built for some of those scenarios that I mentioned, where Microsoft internally had the need to have a highly available and performant NoSQL solution. And so high availability was one of the main design drivers and motivators for how CosmosDB was created. And I want to basically drill down a little bit on how availability and disaster recovery is actually designed and implemented in CosmosDB, because, and that's the last part of I'll go into, that has an impact on some of the cost as well. Like depending, for example, if you say you replicate your data into Azure regions, the more regions you have, the better your availability, of course. But on the other hand, for each Azure region where you provision your data, you also need to pay for it. So there's always a trade-off between the different availability features and the cost of maintaining the service, basically. And so I want to also drill down into the trade-offs a little bit to basically make it easier to come up with the right decisions there. Brief overview of how availability is implemented, basically. What we see here is basically an abstraction on the different replica sets in each of the regions. When you think about a table or a container in CosmosDB, CosmosDB is a schemaless database, so you don't have to upfront define a schema, unlike any relational database. The documents internally are stored as JSON documents, and each document has two basically columns that uniquely identify a document. One is the logical partition key, which is any column a user can choose basically when creating a container, and something called the ID, which is basically you can think about it as a row key. It needs to be unique within the scope of a logical partition. And like I mentioned, most NoSQL databases and as well CosmosDB is optimized for horizontal scale. So the way how we scale is basically when you ingest millions of documents, we will look at the partition key value, and via a hash mechanism, we know basically on which node or machine your data will be located. And when I say machine, it's a little simplification because it's not one machine, but it's actually a replica set. What you see in those in those circles, a replica set is basically it contains of 4 different machines. All of them host the same data. And we have 4 replicas for availability purposes, because each of them stores this. So if one replica is dying, we still have the data available in a sufficient number of replicas that we can maintain, and there's no outage or data loss because of it. And so what we see here is in each of those circles is basically an abstraction of the replica sets that are used to store the data, and then we see the arrows to the replica sets in other regions, like what we see here is the West US, East US, and North Europe. It's just an artificial set of Azure regions where the data is replicated to. It basically shows that there are certain roles individual replicas can take. There's, for example, one replica which coordinates all the write access. So clients will use the leader to actually commit write operations, and then the leader will distribute the work, make sure it's stored on a quorum of replicas, and only acknowledge to the application that the data has been written once it has been written to a quorum of replicas. And then one of the other replicas is the so-called forwarder, which is responsible for basically triggering the replication into other regions. And then each of the 4 replicas can also be used for read access. Yeah, main thing I wanted to land on this on this slide is basically each chunk of data, which is defined by the partition key I mentioned, is stored on a set of replicas, and that's how even with one region there are some high availability guarantees that we can provide. And with replication into other regions, we can, of course, improve the availability even more, because even if there's a complete regional outage in Azure, the data is available in another region, and it's possible to fail over to that region and continue working, basically. Another important like architectural decision when using CosmosDB for certain workloads that needs to be done pretty early and upfront is basically choosing the right consistency model. I'll try to summarize a little bit and don't go into all the details on the slide. That's more for reference later. But the 5 consistency models that we provide is basically eventual, means when you write data and you read it later, it's possible that you get older data, like you don't get the latest version of the document. But eventually, you of course will get the latest version as well, but it might take a couple of seconds or even minutes. With each step going up the list, basically, the consistency model provides better or stronger guarantees on when and how you can read the latest version, basically, when you do a read immediately after a write. With session, for example, we have basically a built-in mechanism that at least the instance that you used when writing a document would always be able to read the latest version of the document. With bounded staleness, you like CosmosDB has two high-level models. I'll go into them later. How write operations happen. The default setup is something called a single master setup, where when you imagine you have 2 different regions, West Europe and North Europe, you basically make one of the regions your write region, which means all the write operations will go to that write region, and then the data is replicated to the secondary region. If West Europe is your write region and for whatever reason West Europe is down or you want to do a failover, you can basically elevate North Europe as a write region, and in that case West Europe becomes a read-only region. With bounded staleness, you basically have a guarantee that when you read, even immediately after a write in the write region, you will have strong consistency, which means you get the latest version of the documents. But the replication to the remote region will happen asynchronously. So it's basically a trade-off between, yes, I want to always be able to read the latest version of the document, at least in the write region, but to allow better availability, I'm okay with doing an asynchronous replication. And bounded means in this case, you can basically provide some limits on how asynchronous the replication may be. So it basically means you have a certain time window in which the replication needs to complete. If you get out of the staleness window, then the write would fail. And then the strongest consistency model is strong, which is basically the same like bounded staleness on the write region, but it also means the replication will happen synchronously. So the write will not be acknowledged or committed until it's replicated in all the remote regions, which obviously has some impact on availability as well as latency. One important thing I just wanted to call out is I also added a read cost factor, which basically when CosmosDB, the way how CosmosDB is charged to customers is in a way where you provision throughput, which means you pay for having a guarantee of a certain throughput that you can achieve basically. And the throughput currency basically is something that we call request units. Like if you insert a document, depending on the size of the document and certain configuration options, the request unit that it costs to insert that document will be basically returned on each response. And what you pay for is basically how many request units per second can you use on a certain container or table. And so the read cost factor I mentioned here is basically for bounded staleness and strong, the request charge that you pay for reading each document will be twice as high as for a session on eventual. And to explain a little bit why that's the case, when you use eventual, let's start with the easiest. When you use eventual, like I mentioned before, there are 4 replicas. When you do a read operation with eventual consistency, it basically picks a random replica and reads the data from the replica. There's no need to make sure it's the latest version. So even if that replica doesn't have the latest version yet, it's perfectly okay and it can return. So it only communicates with one replica. With session, in many cases, one replica is sufficient, and reading from one replica is enough. Sometimes you might need to also read from other replicas to get the latest, like the version that your session token is enforcing. But for simplicity reason, the cost would always be stable with one and the same like eventual. With strong and bounded staleness, it's slightly different because reads need to at least go to 2 different replicas to do a quorum read. Like if you read from 2 replicas and both of them give you a version hint that it's the same version, then you know you've read the latest version already. But if the version hint is different, you basically need to go to a 3rd replica, which is a tiebreaker, and will tell you which of the versions is the latest version, basically. And so for bounded staleness and strong, the charges for read operations are more expensive because you need to go at least to 2 replicas, possibly 3. Okay, some other terminology that I might use later, and I wanted to explain a little bit more. Single master versus multi-master. I briefly mentioned already. Single master means when you have multiple regions, you decide that one of your Azure regions is your write region, and all write operations will go to that region. With multi-master, we also added a way where you could allow writing from multiple regions. Like imagine you have West Europe, North Europe, and West US as Azure regions where your data is replicated. In that multi-master mode, you would be able to write data in all 3 regions in parallel. What that means is there is a likelihood of conflicts, because if you don't use global strong consistency, but any of the lower consistency models, it's possible that in West US and West Europe, somebody modifies the same document, and there's no way to avoid that conflict. So the replication protocol got extended. It's basically a hub spoke model. Where we can identify those conflicts, and those conflicts will be provided in something called a conflict feed, and then the conflicts need to get resolved. There are a couple of default algorithms like last writer wins or something that you can choose, and conflict resolution will happen automatically. But there's also the option to do a custom conflict resolution in those cases. For single master, all of this is not really a topic, because only one region at any given time is the right region, and so you don't have conflicts. Availability zones, another term I briefly wanted to explain. So when you think about Cosmos DB, like we have 4 replicas in each region for each of your physical partitions. And if you have 2 regions like West Europe and North Europe, you basically have your data available in 8 different machines for 4 replicas in each region. Azure also has the concept of availability zones. We also support enabling availability zones. What we do in that case is basically, when you imagine you have 2 regions, we would make sure that each of the 4 replicas in a certain region is distributed across different Azure availability zones. And so it would not only provide you the geo-distribution benefits of 2 different regions, but even within a region, it would spread the replicas across different availability zones and make it more unlikely that more than one replica at any given time gets impacted, basically. Okay, trade-offs, again, mostly for reference. I'll call out a couple of things, but don't want to add too many boring things. But I think this table might be helpful if you really want to implement Cosmos DB at some point, and you need to make those decisions, because it can help basically guiding some of those decisions between understanding the cost impact and the capabilities that you get. The main thing I wanted to call out here is, like I mentioned before, when you enable multiple regions, you get some benefits. Like when we compare, for example, a single region, like the first 2 lines, we see that the best read and write availability is 4 nines. You cannot get better than those 4 nines. You also see that the RPO, like the recovery point objective and recovery time objective, are pretty bad. Like it means that there might be up to 4 hours of downtime. And if you want to increase both availability as well as reduce the RPO and RTO for disaster recovery scenarios, adding a second region is definitely it's like crucial, basically. And depending on whether you use single master or multi-master, it means that your read availability can go to 5 nines in both cases. For write availability, you can only get to 5 nines of availability with multi-master, simply because imagine on a single master, if your write region is down, it takes some time to fail over to the other region so that the other region can accept writes. And because that time window is roughly 15 minutes, and because that's high enough that we wouldn't be able to meet our SLAs, it doesn't make sense to promise 5 nines of availability, because if there's a regional outage, then it means 15 minutes you will not be able to do any write operations. And that's the reason why for single master on write availability, 4 nines is the best that you can get. For multi-master, it's also 5 nines. And yeah, I think I covered that briefly. Bounded staleness is also a little bit special, because you can define the staleness window, like how long the asynchronous replication may take, and by doing that you can limit the RPO, basically the possible data loss by doing asynchronous replication. And then last but not least, the cost factor. If you deploy your data into two different regions, it means the cost will be twice as high in most cases than if you just have a single region. Multi-master is adding another factor. It's basically the price for 100 IUs per second is twice as high as for single master. So multi-master also, it provides the benefit of being able to get better write availability, but it also increases the cost. So it's something that needs to be, there's a trade-off that needs to be made. And yeah, and then availability zones has a factor of 1.25. So it's like, because we are restricted in having to deploy the replicas in different availability zones, the overhead and cost for us is also higher. So there's a factor of 25% upcharge compared to when you don't use availability zones. Yeah, that summarizes the high availability so far. Let me check, was there any questions so far?
If you guys have any questions, you can also raise your hand here in the in these emoticons basically, or you can write in your chat window. We are looking at both of it.
Okay, looks like there are no questions yet, so I'll just proceed for now.
Mm-hmm.
Next topic I wanted to cover, because that's also basically an architectural decision that is changeable. So it's not something that carved in stone. You do it once and you cannot change it. But it's something basically worth considering before even starting to implement a solution, because it helps you to understand what the cost of a solution might be. There are several ways how you can provision the throughput that I mentioned. But what I've said before is basically what you pay for is a guaranteed throughput that we basically reserve for you and that you can use. You pay for it usually, like, except for serverless, which I come to later. You basically pay for the throughput that we guarantee and reserve for you, whether you actually use it or not. Which means, of course, like, there are scenarios where, especially, for example, the commercial scenarios that I mentioned, order management, nearly every e-commerce site has, at least within a local region, has certain time periods of the day where the traffic is much higher than during other periods of the day. So because you have to basically pay for the provision throughput, whether you use it or not, in the original model that business model CosmosDB had, you always had hours of the day where you basically didn't even use the throughput that you paid for, and that was provisioned. So gradually we added some additional offers to basically help customers in those situations where they didn't need to modify the throughput they pay and pay for, and we guarantee multiple times a day, but basically make it easier to get this managed without wasting money on throughput that you pay for, but nobody is using it. And so I'll walk through some of those trade-offs that need to be made when basically defining the SKU or offer that you use for CosmosDB. One option is, like, the default model is that for each table, container, or collection, however you call it, you basically provision the throughput independently, which means if you have if you have two collections or tables, like orders and users in your database, both of them would be isolated containers with isolated throughput you pay for, but that means they would also be stored on completely different partitions. So imagine there's some issue, some replicas down in one of the partitions. It would only impact that one container. It would not impact any other container. And the same is true, like, if you have very high load and basically all your throughput is exceeded on one container, like, let's say the orders, it means the second container is completely unimpacted. You would still be able to use it even if the other one is overloaded. But it also means that for each container, you have a certain minimum throughput you need to provision, which is 400 request units per second, which basically means you would be able to insert, for example, 81 kilobyte documents. Many customers had scenarios, especially on the Mongo API, where they had a large number of containers. Like in your database, you had 20 different collections or tables. Many of them pretty much had no traffic at all, or very, very low traffic. And so having to pay for the 400 IUs, even when you basically never use it, was a problem. So the option that we introduced was, instead of provisioning your throughput and guaranteeing your throughput on just a container level, you are also able to do it on the database level, which means all the containers within that database basically share the same throughput, which means if the throughput is exceeded, it would also impact all the containers and not just the one. There are a couple of limitations. This only works up to 25 collections by default. If you have a database with 50 collections, by default, it doesn't work. You can create a support ticket to increase the number, but it's not really recommended, because at that point, it often can cause problems, basically, because there's no isolation anymore. Those are the main limitations. My usual guidance when discussing this with customers is that shared database is often a good idea for non-production scenarios, like development or test scenarios, or for containers which basically contain metadata, which are often read only once or every couple of minutes. So where the throughput is significantly lower than 400 IUs. If you have more than those 400 IUs that you need for a container, it's usually better to have dedicated throughput provisioned. The next one I wanted to briefly touch on is autopilot versus manually provisioning the throughput. The default model that we had was basically for each container, you would need to decide how many of those IUs do you need. You were able to change it. So like imagine like in Xbox, for example, at 8 p.m., wherever the region is, the load was much higher than at 8 a.m. So there were possibilities to basically change the throughput every hour or dynamically, basically, depending on the loads that happened. But of course, that's a lot of work for customers, and most customers said, "Hey, why can't you do this automatically for us?" So we came up with this autopilot offer, which basically can dynamically scale the throughput that's provisioned and that you need to pay for. You basically only define a maximum throughput that you would allow, and you don't want to ever exceed that throughput. And between 10% of that maximum and the maximum, we can dynamically scale the throughput that's necessary. And then whatever the highest throughput of in the interval of an hour is what you would get charged for. From a business model, the only thing to consider is that 100 IUs per second with autopilot enabled is 50% more expensive than when using manual throughput mode. So financially, it's only interesting if the load variant across different hours of a day, for example, is high enough so that you end up with a cheaper solution. For multi-master, it basically doesn't matter. For multi-master, you can always enable autopilot without any extra cost. So for multi-master, I think autopilot enabling it is a no-brainer, and is more or less done automatically. Last but not least, an offer which is currently still in preview mode is the so-called serverless offer, which is basically the only offer where you don't need to pay for the throughput that we guarantee and reserve for you, but instead you only pay for the throughput of the request that you actually make. So if for 10 hours you don't do a single request to your database, then there would be no charge for those 10 hours. And if you have bursty traffic where for the next hour you have thousands of requests, you would only need to get charged for the request units in that hour period. But there are certain limitations, like it doesn't scale unlimited because we cannot reserve, of course, unlimited capacity. So the main scenario for serverless, I think, are non-production scenarios or starting to play around with CosmosDB. For scenarios where you want to store terabytes of data, it's not the right offer, because in that case it would also become too expensive. Because of course the IUs when they get charged not by what we provision, but by what you actually use, the IUs are also more expensive. Last but not least, there's basically financial way to save some costs. Similar like for VMs, there's a like something like reserved instances, where if you commit for at least a year to use a certain amount of throughput, depending on either account level or on a subscription level, you get certain discounts and by doing a pre-commitment, basically. Very similar to VMs. It can be pretty significant, like between 20 and 65%. I just kept the slide here, so if it's interesting for anyone, it's something that can be followed up on later, but it doesn't really have any technical implications. Okay. Yeah. Next part would be Cosmos DB APIs. Again, if there are any questions, just let me know. Otherwise, I'll proceed.
For now, I don't see any questions in the chat. I think we can proceed.
Okay, I just wanted to provide a little, very high-level overview of how do we achieve this thing with multiple APIs. Like what I mentioned before is our SQL API is our actual core API. We also have ways where you can use the table, like Azure Table Simulation API, basically, or Mongo or Cassandra. So how is it implemented, really? The main thing I want to get across here is basically when you think about it in a mental model, all these APIs are abstractions only on the wire protocol. So what happens in the back end, like how the data is stored and how our own service endpoints, like our own compute nodes on the server side, communicate with the store and the backend nodes, is identical like in the core SQL API. What we do is basically when you use a Mongo or Cassandra or table API, we basically inject a compute node, which is also hosted on our Service Fabric clusters, that will basically do a translation between whatever the wire protocol is, like Mongo, Gremlin, Cassandra, or table, into the core API. And this is also part of the reason why when you go through, I actually reference them in the next slide, we have a feature compatibility list, especially interesting for folks using OSS APIs like Mongo or Cassandra. We support a good chunk of the wire protocol of Mongo or Cassandra, but there is no hosted Mongo or Cassandra. So the behavior is not identical. What happens is we allow you to use a Mongo driver or a Cassandra driver, and most of the features will work. We document which features have constraints or don't work. But the important thing is the behavior is not identical because it's not a hosted instance of Mongo or Cassandra, but it's just a compute endpoint which basically translates the protocol and then uses Cosmos DB under the hood. That is especially when migrating applications that used native Mongo or Cassandra, for example, on-premise, you want to move it into the cloud. It's important to have that in mind because the behavior might be slightly different than what you see with native Mongo and Cassandra. And with behavior in this case, I mean efficiency, performance, and also checking the feature compatibility list. But it also comes with some benefits, like you also have the option to just replicate the data in multiple regions, which is much harder, for example, on Mongo. It's possible as well, but the geo-distribution capabilities of Cosmos DB are in many ways better than what native Mongo would allow you. Or when you do it on premise, it is associated with a really painful administration and management overhead. So there are some pros and cons of this model where the Mongo and Cassandra or table and Gremlin abstractions are just compute endpoints that do the translations. It's important to understand it's not just a hosted native whatever Mongo or Cassandra, but it can work in several scenarios. It's just something to take a look at. Yeah, going through like the decision map, basically when to use which API. Basically, I'm like for each scenario that's a case-by-case decision, but I want to just provide some usual trade-offs or guidance, basically. In general, my recommendation would be to use the SQL or Core API in most new applications, like greenfield applications, simply because it allows access to new features, to all features earlier. Because, like I mentioned, without it being available in the SQL or Core API, even our Mongo, Gremlin, or Cassandra abstractions couldn't even use it, because under the hood they also use the SQL or Core API. And because there's not an additional compute hop injected, it's also cheaper in most cases, because there's no compute overhead that also somebody needs to pay for, basically. And yeah, the last point I've covered before already, like be careful, just because it's called the SQL API, it's not a relational database. So when migrating relational databases, you will pretty much always need to look at the design and data model to be able to migrate it so that it works well. Gremlin and Graph. The interesting thing with Gremlin is that the data that's actually stored are just the same way like the SQL API which would store the JSON documents. So the Gremlin API is the only one where you can basically have a mix, where when you create a container and you say, hey, store my data in an orders table, where you can both use the Gremlin API as well as the core SQL API to later read or modify documents. Basically, depending on the needs you have, you can use either API. For all the other APIs like Table, Cassandra, or Mongo, you decided when you create the container, but then you have to stick with that API. So you cannot say, hey, I want to ingest using the SQL API, but I want to read or query via the Mongo API. That's not possible. The only case where there's some bandwidth where you can mix it is a Gremlin or Graph API. Table is it's really a thin wrap. Like Azure Table was a service that was built in the Azure Storage Core service. It's also a NoSQL database. Basically, it only has a subset of capabilities or features, and in that case, it was relatively easy to basically implement the SDK based on the SQL API. So under the hood, it's completely using SQL API, JSON documents. It's just an implementation of the Azure Table SDK that is, or the endpoint, so that the SDKs can talk to it. But under the hood, it uses CosmosDB, and it has some latency and availability advantages. Like Azure Table was not very good at providing predictive latency. For example, if something like splits needed to happen in Azure Table, it could take up to minutes. So latency was not very predictable. But Azure Table is also much cheaper because the data isn't stored on SSDs and on 4 different replicas. So even today, some customers still use the old, basically Azure Table service, simply because if they don't need the better latency, then it's still cheaper than using the Table API via CosmosDB. In general, I would say for new applications, there's really no reason to go to the Table API, because the native SQL or Core API provides more features to more efficiently. The Table API is really only something if you want to migrate an existing application that uses Azure Table already, but you need some better availability or latency. Then it's something to consider to just use the Table API, because you don't have to change your application. But for new development, I think the SQL or Core API is always a better choice than Table API. Cassandra and Mongo both are basically making a pretty decent percentage of our customers. Mongo, for example, is nearly 30% of the revenue that we make. So it's a very frequently used API. So I'll drill down into those two a little bit more. Cassandra, for everyone who doesn't know it yet, I think Theo, a program manager on our team who's working closely on Cassandra, will or has already held a presentation during the meetup in Frankfurt, and will drill down into Cassandra a little bit more. So I'll keep that pretty short. But Cassandra is also a NoSQL database. Differently than CosmosDB and Cassandra, you have to upfront define a schema, which means there are some optimizations, like especially when you store the documents, that you can take into account because you know the schema already. You can imagine, like, if you have a JSON document with 100 different properties, storing the property name every single time in each JSON document when you store a couple million documents is not very efficient, because like 30% of the data size that you store is basically just the property names in your JSON document. It's necessary if you really want to be schemaless and have different schemas, but it's also very clear that there are more efficient ways to store data if you know the schema up front. And for Cassandra, that's something even in our core implementation, because for scenarios where we know the schema up front, we will also store the document not just in plain text JSON or compressed JSON. It's basically a special binary format that allows to store data much more efficiently than with the core API. And overall, that for Cassandra is one of the benefits, especially in storage heavy scenarios. Cassandra also right now is our best option in scenarios where you have hybrid scenarios, like you want something to happen on premise, you also want it to happen in the cloud. The reason for that is that with Cassandra, we have two capabilities which are pretty unique. One is called CCX, which basically allows you, imagine you have a Cassandra cluster on premise and you want to also have the data available in the cloud. What CCX allows you to do is basically, it's basically an endpoint protocol that allows the Cassandra API in CosmosDB to participate in the replication protocol that Cassandra on-premise would have. So you can store your data on-premise in your Cassandra API, but the replication would also happen into the Cassandra API in the cloud. So the data is also available in the cloud. And depending on where you process your data, you might be able to either use it in the cloud or on-premise. And for Cassandra, we also have a new preview feature, which is called Cassandra Managed Instance. In that case, unlike all that I talked about before for the different APIs in CosmosDB, it's not actually just a translation on the wire protocol, but we actually host like native Cassandra instances for the customer. So it's basically a hosted Cassandra option natively, which is necessary for some customers, like what I mentioned, Cassandra and Mongo. Both we have published the list of supported features, but it's not identical to Cassandra. So if you have applications that you need to transfer into the cloud that have some hardcore dependencies on Cassandra, and some of those features are not available in the Cassandra API, then the Cassandra Managed Instance is one option, so that the applications can actually talk to native Cassandra and rely on all the built-in behaviors. But it's still possible to also replicate the data into a Cassandra API, and you can basically do the transition into the Cassandra API more slowly and change applications in a slower factor. Yeah, but what I mentioned, like in Cassandra, I think overall the user experience is often pretty well, because like the number of features that are not supported is relatively low. And Cassandra, unlike Mongo, also has a pretty narrow scope of operations that you can do. Like one thing I always be a little bit careful is Mongo itself has a very wide scope of functionalities that allows you to use it, which is good on one hand. On the other hand, it also allows you to do things that can, for physical reasons, never scale well. So it's very easy to shoot yourself in the foot, similar like with relational databases with SQL. Cassandra is much more constrained in the surface area, and so even lift and shift scenarios usually work pretty well because the scenarios often translate very well to what CosmosDB under the hood supports as well. Yeah, Mongo, like I mentioned, is a pretty huge contributor to our user base as well as the revenue. We have added Mongo versions up to 4.0 right now. They're like the native Mongo has later versions like 4.2, for example. What the latest version that we have right now is 4.0. With each version, basically Mongo adds new features. And for each of those versions, I linked the feature compatibility metrics here. There are certain areas, like I mentioned with Mongo, where the surface area is very wide. Some of those features we intentionally don't support. For some, it's just a gap where features are not available. The two main scenarios where I would be careful if you want to basically migrate an existing Mongo app to the Mongo API in Cosmos is any usage in the aggregation pipeline is worth double checking. Because in the aggregation pipeline, I would guess we support around 60 to 70% of operations, but there are a couple of them that are not supported. And then with Mongo 4.0 and 4.2, native Mongo introduced the concept of distributed transactions. In 4.0, that was pretty much only for Mongo databases that weren't charted and only within a container. But for 4.2, it basically they tried the attempt is to extend distributed transactions in Mongo, which is also a NoSQL database, in similar manner like it's possible in relational databases. And that is something where we will also add some support, but distributed transactions will always hurt, especially massive scale scenarios. And so there will be trade-offs. And so if that's something you have a hard dependency on, I would be very careful by looking at the Mongo API, and there might be other and better options to use native Mongo, either hosted in IaaS or there's also the Atlas Mongo hosted service in Azure available that might be a better fit than using the Mongo API in cases where those distributed transactions especially, but also some of the aggregation pipeline features are critical for you. Okay. I'm done with the presentation mostly, except for some of the data modeling best practices. This gets a little bit more technical. So if we have any questions or like whether something was unclear, where for example CosmosDB would be a good fit versus not a good fit, I think it would make sense to discuss it right now. Otherwise, I can spend as much time as we still have left going through some of the data modeling best practices.
We'll see if somebody is asking any question, but until then, I have a question. You mentioned that it's recommended to, the default recommendation is to use SQL or core, although it's not SQL, so to speak. It's yeah. What would you say? What are the scenarios where you should be really, really careful on not using other APIs? For example, Cassandra or Gremlin or Mongo, for example, where you really have to be very careful on choosing between them.
So I think the higher the demand for scale and latency is, the better the native API will. Like the native API simply has one hop less. Like it's going through one compute node for the translation less, which means ultimately your latency is better. And the RU charges for certain operations are also lower when you use the SQL API. The other things are there are certain features that will be available in SQL first. For example, like one of the new preview features that we have right now is AAD authentication. It will come to Cassandra and Mongo API at some point as well, but it will come later. It comes to the core API first. Another feature that is super useful in certain scenarios, especially what I mentioned, the digital twin scenarios, for example, is the change feed. CosmosDB has a built-in feature, and I'll get to that in the data modeling part later, which is called change feed, which basically means if you insert documents, you also automatically have a view which you can think of as I would say it simplified as a queue, like a stream of events in the order of which the events happened, similar to like if you would add the documents not just to a database but also to Kafka or Event Hub. And that allows you to build event-driven architectures by only storing the document once, but using the change feed feature to also get the events and process them and push them to other microservices. And that is also like the first 2 years only available on the SQL API. Right now, we've added support for it at least partially in Mongo and Cassandra as well. But some of those things will just take longer and have more overhead.
Okay, understood. Good. Do we have any other questions, guys? Okay, then I think we can move to the data modeling part of it again.
Okay.
Yep.
Okay. So I think the biggest decision that needs to be done when looking at the data modeling for a NoSQL database, but also especially CosmosDB, is basically choosing what to use as a partition key. Like I briefly mentioned before already, the partition key is basically used to identify on which physical set of replicas, so machines, your data is located. And the partition key, like the way how the routing basically to the right physical instances works, is that the partition key is a certain property in your document. You can define which one it is, and then the hash value of whatever the value of that property is used to define where your data is located. And it is critical for several reasons, because when you imagine we support horizontal scale. So if you store like 10 million documents, they are distributed across a number of sets of 4 machines with replicas. So what you ideally want is that your data is distributed pretty equally. So both from a storage perspective, like imagine you have 10 of those replica sets. If you have stored 10 million documents, ideally each of the replica sets has 1 million documents, so that the storage is balanced equally. And even more importantly, your load access pattern, like if you insert documents, you query them, you read them, should also be distributed equally across all of those partitions. Because if that's not the case, then you pay, let's assume for a container with 10 of those partitions, like 10 replica sets, you imagine you say you have 100,000 request units. So if you have a scenario where your load or your data is skewed towards a single physical partition or 2 of those physical partitions, it means those physical partitions might be at a point where they exceed all the throughput available. Like if you imagine the 100,000 IUs on a container with 10 partitions, it means each partition gets 10,000 IUs. So you might have scenarios if the load is skewed where one partition is running hot and cannot process more data because your throughput is exceeded, but the other 9 partitions are still bored and are idle basically. And the fact that you pay for the throughput available in all 10 partitions means you are basically wasting a lot of money because some of the partitions are doing less work than the one that's a hot partition. And so for different reasons, not just for technical and performance reasons, but also for cost reasons, it is pretty critical to come up with a partition key which allows a reasonably well distribution of data as well as load across different partitions or shards. And I would claim this is the case for all the NoSQL databases, whether it's Cassandra or Mongo. When you use sharding as a way to enable horizontal scale, then making the decision on how you shard your data is one of the most critical decisions in your data modeling, and one that drives data models that are differently than in relational databases. Yeah, briefly going through how does it work basically. So imagine you have a JSON document where you have a user ID property and you want to choose that as a partition key. Like I mentioned, how it happens under the hood is basically the hash value of that user ID value is calculated, and based on the hash value, we know on which physical partition it is located. If you store more data, it might be relocated. So basically, the fact that user KBNM, like my user ID, is located on partition 3 is just a temporary assignment, because if more and more data is introduced, you might get a higher number of partitions and it might move to a different partition. But by hashing the partition key value, it's always possible for us to locate on which partition data is currently located, basically. And on which of those partitions it actually is located is completely ambiguous to the user. The user doesn't need to care about it, but the partition key is the only way how you can influence that the distribution is happening equally, basically. Yeah, this is an example, for example, where we see partition 2 gets pretty hot, because like we see partition 1 has a couple of users, partition 2 only has one user, all the others are on partition N. So in this case, your data would be pretty skewed around a certain partition, which usually is something you would want to avoid. And to make that decision, it's usually something where you really need to understand the use case pretty well. So it's not something where you can come up with some magic wizard which will always find the right solution. It's something where you need pretty detailed knowledge about your use cases. Also, what type of queries will be executed later, so that it's possible to make assumptions there. Yeah, this something we covered already. Yes, like I mentioned, distribution is important. Yeah, one of the important things when going through this and when doing the data model, it's important to have a rough ballpark of both the data size of all the documents that you expect to store, as well as the throughput, like how many inserts, updates, deletes, or read operations you expect to happen per second, basically. And having a ballpark is perfectly sufficient, but that's important because some of your data modeling decisions will depend on it, basically. Yeah, one other thing is it often makes sense to do like small prototypes to get a better understanding, especially of cost estimates. The good thing with CosmosDB is if you do any point operation, like you insert a document, you update a document, you read a single document, all of those operations and the request charge are independent of the total size of your container. So whether you have 10 documents in your container or you have 10 billion documents in your container, each individual point operation will cost the same, like in request units. For queries, it's a little different because like index size, for example, will influence how many IO operations are needed, and the request charges for queries, like when you run a SQL query against the container, will depend a little bit on the size of the overall container. But it often a prototype, even if you don't have the full data set ingested, still helps to get at least a ballpark. And then one of the things I think is the most common mistake that we see when talking to customers. Many customers are afraid of using a partition key where you have many unique values. While in theory, on the contrary, it's perfect. Like for any write-heavy scenario, when you do a lot of writes, it's pretty much perfect if your partition key is a value that's unique, like the ID, for example. Like you have a GUID as a value, it's perfect because you will always have a perfect distribution of data. If you insert 10 million documents, they will always be very well distributed across physical partitions. So There are a couple of scenarios where it might be better to have partition keys which are like not the unique key, because if, for example, if you query for all data of a user, it makes sense if the user is kind of your partition, because in that case your query only needs to run on one partition and not across all machines to find the data in each of the partitions. But depending on your use case, if you are either very write heavy or those queries are not super latency critical, even in those cases, using a unique key might be good. And often it's a compromise where you basically need to understand what are my typical query patterns, which of these queries are mission critical so that I need to optimize for it. And then how can I use a partition key which still has enough unique values so that I get to a good distribution, basically. But my personal recommendation is I would always start with ID, so the unique value, and then make the decision, why would I not use it? If you, for example, if 90% of all your requests are queried by orders for a user, for example, then using the user as the partition key would probably be better than using the unique ID. But basically starting with ID and then making decisions based on the known query patterns and how critical those query patterns are to decide why not to use the ID often leads to better results than starting to optimize around some queries, even when queries only make 10% of the overall workloads that you have later. Yeah, there like one of the things that's often asked is like, yeah, you mentioned you have physical partitions. Basically, you chunk the data in a container, and you do this dynamically. So if you ingest more and more data, you increase the number of partitions and chunks. One of the questions that comes up often is when do you split? Basically, when do you decide that you need more partitions? There are certain limitations, both for storage as well as throughput, that an individual physical partition can hold. Those are implementation details. So I called them out here, but they might change in 4 weeks or in 4 months because we use different physical abstractions or SKUs or machines on our end. But there will always be some limit when the split is happening. And right now, the storage size a single physical partition can have is 20 GB of data. And the maximum throughput is 10,000 IUs. So imagine if you store data, like if you store 50 GB of data, you will have at least 3 partitions because each partitions can only hold up to 20 GB of data. Same is true if you provision 100,000 IUs on your container, you will get at least 10 physical partitions because each of them can handle at most 10,000 IUs. And so those are just things to keep in mind as a ballpark to make decisions. But like I mentioned, its implementation detail could change, and you don't really need to know the exact details because when splits happening or the execution of splits is all something that's happening transparently without you even recognizing it. Yeah, here's a brief example. I'll go briefly about it through it, but basically a scenario where an IoT scenario where cars, like as devices in an IoT scenario, are storing events and sending them. They're supposed to be stored in CosmosDB. And so the couple of candidates of choices that were looked at for different partition keys were the vehicle model, the current time when the event happened, the device ID, which would be basically a unique identifier for each car, and then a composite key where you basically you create an artificial property which contains both the device ID and the current time. And one thing to kind of make the trade-offs is to look at the storage and throughput distribution if you use this as a partition key. What we see with a vehicle model is that there are certain vehicle models, and the same is true, for example, in multi-tenancy. If you use tenant ID as a partition key, you will pretty much always end up in a similar situation, that you will have certain models or tenants if your partition key is more frequently used in them, where you both have more data as well as more throughput, because like the Prisma is the most sold vehicle, so you have more of those vehicles. That means more events stored, and you will also have more throughput because more cars will insert data than for other models. So the vehicle model is a very bad choice because both storage as well as throughput is heavily skewed. Current month, if you use it and you look at the storage distribution, you basically get a perfect distribution pretty much, assuming that every month roughly has the same number of events from all of those IoT devices. But when we look at throughput, it's absolutely horrible because like all the events are usually stored and ingested at the current month. So the current month, whatever the current month currently is, will always have much more throughput than any of the other months. And assuming you store all the events in one container, this will result in very high cost because you basically have to provision so that whatever the logical partition for the month has enough throughput, but you're not using it for any of the other partitions. So it will automatically result in a very expensive solution, basically, which will probably cause frustration. Next one is basically looking at the device ID. So basically each car has its own. We have a partition, and this is basically what I mentioned before. You choose a partition key where you have a large number of unique values. When you look at the storage distribution, you see it's reasonably well distributed. For throughput, it's also reasonably well distributed because each car might send events every minute, and some cars might be in a bad state sending more events, but it's not completely out of the ordinary. When using a composite key, things are a little interesting. Basically, you still have the storage distribution, which is very well. For throughput, you see that certain logical partitions, always the logical partition for each car with whatever the current month is, will see higher throughput than for all the other months. So you still have some skewness, but in this case, I would still say the composite key would still be a doable option, because when we imagine we have 10 million cars, it means we would have 10 million logical partitions for each car the current month, where we see more throughput than for all the other logical partitions. But because the number of partitions with equally high throughput, like even there is a skewness, it's the number of logical partitions with high throughput is still very high. It means when you build the hash codes of all those logical partitions and you distribute it across whatever the number of physical partitions is, overall your load will still be pretty well distributed. So the composite key or the device ID would both be options that would work pretty well from a distribution perspective. Yeah, the granularity, I touched on that. The higher the granularity, the better. Like the more unique keys you have, the better as a shard or partition key in general. Yeah, one other feature that's also going to come to CosmosDB pretty soon is something called subpartitioning. This is an interesting feature, like when we go back basically, or in our mind, to the candidates for partition key. One of them was the vehicle model. Vehicle model was pretty bad because we had too few logical partitions, and there were some few partitions, like for the Prisma, where the load, the storage and load would be very high because that's a top selling product basically. But with subpartitioning, you would have a way where you could say, hey, use the model as the first part of my partition key, and then the device ID as the second part. What would allow that to do is basically, the logical partition would be combination of both fields. So you would have an equally well distribution of load and storage, like we had with just using the device ID. But also device ID documents would be co-located on one or multiple physical partitions, because like all the device IDs for a certain model would be basically co-located on a couple of physical partitions. And the benefit of that sub-partitioning over just using the device ID is if you have query patterns where you only know the model and you want to get all the data or aggregates over the data for a certain model, it means we basically under the hood know that there's only a subset of partitions that would store documents of devices for Prisma, because we can basically tell they are co-located and it's only a range of partitions. It's not the full set of partitions. And that means when you look at query execution, it would be more efficient because you know that you only have to talk to three replica sets, not to all of them, basically. So the query can be significantly more efficient. And so with subpartitioning, that will allow some new options on partition key choices. We expect it to be rolled out later this calendar year, basically in the second half of the calendar year. Yeah, brief summary for partitioning is basically a good partition key, like I mentioned, is expected to have a good distribution, have usually a large number of unique values, and the only thing to consider there is what are the typical query patterns that might drive not using a unique value, for example. Okay. Any questions to the partition key, like choosing a partition key or around that? The partitioning, was anything unclear or are further things necessary?
I think the example that you shared was pretty interesting. The one question that I had there was, so basically you said distribution is one of the biggest things that you should consider while selecting the partition key. Is that correct?
Correct. It's like if we go back in the sample, if you use something like the vehicle model where both the storage and load is very skewed, there's basically, once you make that decision, there's really nothing that can result in a good user experience, because you will have a lot of resources that we need to keep to provide you the guaranteed throughput, but you will never ever use it, and so the cost will explode. And one of the things why I spend so much time on partitioning is really, if you make a bad choice with a partition key, it's basically irreversible. You basically have to create a new container with a different partition key and then re-ingest the data. It's not like you can change the partition key. It's not like changing a primary key in a SQL database, because it's all sharded. It's distributed across so many different partitions. It's not something that we could change atomically, basically. So it basically means starting from scratch again. And so
you really need to be clear about your use case and how the queries could be, or how the pattern could be, basically.
Yeah. And it's really worth spending some time on it and even prototyping it, because it is a significant decision. And I would claim, again, this is the same whether you use native Cassandra or Mongo. It's all very similar, because the sharding concept is the same. It's optimized for horizontal scale, and that means you need to have a way to basically balance between shards reasonably well. It doesn't need to be perfect, but in a reasonable way.
Yeah.
And there are several patterns like how this can be achieved. I have a couple of them later, but I think from a time perspective we won't be able to get to it. But they are in the slide deck. So if people are interested, I used a couple of walkthroughs of typical scenarios that we see, where I drilled down basically into how can you model the data, even when it's not very intuitive, maybe initially, so that you get to a partition key that's reasonably well distributed, but you can still get your data pretty efficiently.
In this case, if I shortly jump back to your example, what could be the reason to select this? You had the ID plus time, this composite key. what could be in any scenario the reason to have composite key over device ID as a partition key? Could that be any scenario where that is better?
So one scenario would be, for example, because like I mentioned, there are certain limitations on how much data you can store in a logical partition. Imagine you have some devices which are pretty hot and you would need more than 20 gigabyte of data for a single device. In this use case, it wouldn't happen, but that's one way where you might want to have a composite key where you basically allow spreading what otherwise would have been one logical partition across multiple, so that they can be spread across multiple physical partitions or shards.
Okay, understood. Yeah. Okay.
Okay. Yeah. Next brief topic I had was indexing. I'll try to shorten some of it because I think we only have a couple of minutes left. But indexing, the main point I wanted to bring across, like unlike any relational database, indexing is not like indexing implementation is very different than in relational databases because we don't know the schema upfront, basically. So the way how the indexing is stored and used or processed in CosmosDB is mostly around a kind of a special tree structure that allows us to filter efficiently and store those indexes without knowing the schema upfront. And by default, and that again is one of the kind of cost or efficiency related topics, by default, when you use the SQL API, indexing will index every single property in your JSON document, which of course means you can query by any property pretty efficiently. But there's also some cost associated with indexing a property in a JSON document. The cost in this case is if you insert a document into CosmosDB, like a 1 kilobyte document without indexing, it would be around 5 request units for a 1 kilobyte document. For each property in your JSON document that needs to get indexed, there's a fragment of an IU, like I think it's around 0.3 IUs for each property that you index. So if you imagine you have a JSON document with 1,000 properties, you index all of them, the IU charge for inserting or updating this document will be significantly higher than if you reduce the number of properties that get indexed. And so if you don't need the capability to be able to query for each property via an index, then defining a custom indexing policy where you, instead of blindly indexing every single property, you define that certain sections, like you can, for example, say that a sub-document basically based on a JSON path should be indexed, or you point at individual nodes in the JSON document via JSON path expressions that should be indexed. You can reduce the cost of updates and write operations pretty significantly. And in the Mongo API, for example, that is how it's done. Like in the later, like Mongo 3.6 and 4.0 will not index anything by default. And Mongo API, like the Mongo protocol or driver, has a way how you can define indexes. And that's something that you can use to define which properties in your document should be indexed. And it's an opt-in, basically. While on the SQL API, it's an opt-out. And so that's one of the more common things where customers basically, because it wasn't very intuitive, like we cannot really change the default behavior of indexing every property after it was done initially because it would be breaking. But in hindsight, I think it would have been better to also start with an opt-in model, because otherwise you often end up scenarios where the request charges are higher than absolutely necessary. And so one of the things is also, when thinking about the data structure or data model, is it doesn't make sense to have either a section of your document that contains all the index properties, or do you want to do it in an individual indexing policy, or do you really need a kind of free-form query possibility where every single property is indexed? Because that can also have impact on efficiency and cost. Yeah, this is the tuning of the indexing policy. Point lookup versus query is also another point. Like pretty much every NoSQL database, as well as CosmosDB, have individual operations like APIs to do point reads. Like if you know the partition key and row key, there's a read item in the .NET SDK, for example, API that you can call. And that is actually more efficient than if you run a query where you say select star from C where ID is equal to the row key and the partition key is equal to the partition key. Why is that the case? Because if you run a query, it basically runs through a different compute hop, which executes the query for you. When you do the point operation, it goes directly to the backend node and gets the data from the storage, basically. And so in those, the point lookups are always more efficient, like from a latent, like for point operations, we provide an end-to-end latency of 10 milliseconds. For query, we don't. So if you use a point read, it actually means you are under the latency SLA. And it's also cheaper. So in many cases, when you look at the possible queries that you have, or especially for read-heavy scenarios, it can make sense, even in the data modeling, to make sure that for your most common queries, you can actually serve them by doing a point lookup. Like an example that's also in the slide deck, I'll very briefly summarize it here. If somebody is interested, there are a couple of slides walking through it. In the scenario that I mentioned with the Xbox licensing, one of the most common queries there is basically, does user X own, or is user X allowed to play a certain game? And initially, that was the data model. To answer that question, we had to run queries all the time. And even for an internal team, the cost of using CosmosDB in this case was pretty high. And so we had to do some optimizations. And by changing the data model pretty slightly, and I've basically, I'm going through in the slide deck what we did. We were able to, instead of that being a query, make it a point lookup. And that and some other optimizations helped us to reduce the cost to less than 30% of what it was initially. And the point lookup versus query was not the only optimization, but it was certainly significant in the form of 10 to 20% cost savings just by basically making small changes to the data model. And so that's also something to keep in mind. And I think that's true for Mongo and Cassandra as well. By using the core point lookup APIs, it's more efficient than running a query. And so making sure the data model is maybe usable via point lookups for the hot scenario can be a good thing. Okay, then the data model common patterns. I'll skip over it. Like I mentioned, it's very verbosely expressed. So I think it's okay just reading the slides. And if somebody has questions offline, you can also reach out offline to me. My email address is in the end of the slide as well. One other very brief aspect I'll try to summarize as well is in many NoSQL databases, one thing you have to make a decision on, like imagine you store an order document. You will also have order line items. And there will always be the decision, do you store the order as a separate document and each line item as a sub document, so as an old document? Or instead, you store one order document that contains an array of order line items and everything is stored in one document. You have the freedom and choice of doing both, basically. So you have to make a decision at some point. And there are, of course, trade-offs, but in general, the efficiency, both from a latency as well as on a U-charge perspective in CosmosDB, is best if your documents are smaller than 1 kilobyte. If they are growing, the request charge doesn't grow linearly. It's sublinearly, but it will grow with the size of your documents. And so one of the main criteria, in my opinion, to decide, for example, when you have something like an array, like order line items, do you include it in the document or do you put it in separate documents, is how often do you update or modify all of those array items together? In the case where, in most cases, you update all line items, like, for example, you have some state, and whenever the order goes into a paid state, you would update all line items anyway. In that case, it would probably be more efficient to keep it in one big document. But if you have scenarios where your array items are added or modified basically occasionally or at very different frequencies, having them as separate documents can be better, because in that case you have smaller documents that get updated frequently, and those frequent updates would be cheaper than if you would have to update always a bigger document. And so this whole decision whether to inline or not array items, one important aspect is to basically look at how often are those array items updated together, basically. Okay, change feed, I'll skip for now. Don't think we'll have the time for that. So yeah, last point, I mentioned both the contact for Theo and myself. Theo is a program manager, also living in Europe. He's in UK. He is closely working on the Cassandra API, but can also help on other scenarios. And I'm also, like, if anybody has questions later for a certain use case where they want to get some opinion on or discuss something, have questions, feel free to reach out and we can get into contact offline as well. That would be it from my side. If there are any questions, feel free to raise them. Otherwise, I think I'm done.
Thank you very much, Fabian. If there are any questions, you can ask them right now, or if you want to